All right, welcome everybody, and thank you, Brittany, for that great introduction. So yeah, welcome to Understanding and Recognizing IPv6 Addresses. We have a very compressed, limited time frame here today for this webinar. So like the title is about, not going to teach you about how IPv6 works or how IPv6 routing protocols work or all that stuff. This is just a basic understanding of what an IPv6 address looks like, how to formulate one yourself, how to go back and forth between the binary and the hexadecimal, and the different kinds of IPv6 addresses. We're going to talk about link local, global unicast, multicast addresses, and a whole host of other ones. So with that being said, let's just go ahead and jump right into this here. I'm going to erase, actually don't care about erasing that. Let's just do a whole new whiteboard. All right, so here we go. So you probably know, or the majority of you watching probably, if there's nothing else that you know about IPv6, you probably know that an IPv6 in binary is 128 bits long. So the idea was it's 4 times as long as an IP version 4 address, which gives you almost infinite possibilities as far as how many IPv6 addresses you can have. So let's just start out with our basic binary right here, and then we'll learn how we can convert that. So in the world of IPv6, if you're a computer or a router or whatever, it looks something like this. And I'm actually putting some thought into this for a reason, at least for the first several ones here. All right, so I'm not going to count this up. Let's just assume that, we don't need a 9 in there. Let's just assume that that is 128 bits of binary. All right, so that's how your computer, that's how your smartphone sees its address if it's doing IP version 6. Okay, now we as human beings, though, we can't deal with that. We have to represent an address in something we can actually talk about and write. Now, in the world of IP version 4, which was 32 bits of binary, we took those binary bits and we converted them into what was called dotted decimal notation. The developers of IP version 6, they decided, nope, we're not going to use dotted decimal. Instead, we're going to use hexadecimal characters. So I don't want to make any assumptions here, so let's just do a quick 30-second review of hexadecimal. All right, so for those of you who it's been a while since you've dealt with hexadecimal, hexadecimal is a base 16 counting system. All right, so we know that decimal is base 10, binary base 2, hexadecimal base 16. So what that means is that if I just do a comparison here between decimal and hexadecimal, please forgive my sloppy handwriting here. So with in both scenarios, right, if I give you a 3-digit number, right, in decimal and hexadecimal, the first position is what we call the ones position. So that's the same in both. Here's where we have our variation, our change. So in decimal, because it's base 10, every slot of our number is some multiple of 10. So the next slot would be the tens position. Then we'd have 10 times 10, which is the hundreds position. And we could keep going from there, the thousands, the 10,000s, and so on and so forth. Well, in hexadecimal, because it's base 16, we're in increments or multiples of 16. So we've got the ones position. The next slot in our 3-digit number is the 16s position. Then the next one would be 16 times 16, which would be 256. And we could keep going. The next one would be 256 times 16, whatever that is. Okay, here's the next difference. In the world of decimal, each one of these placeholders here could hold a digit from 0 to 9, right? So those are our 10 values we can select from. So for example, I could have 1, 3, 1, which stands for 1 times 100 plus 3 times 10 plus 1 times 1, which gives us 131. Now in hexadecimal, because it's base 16, our first 10 digits are still exactly the same as decimal. We still have from 0 through 9 for our first 10 digits. But then we still have 6 digits left to go because it's 16, base 16. So now we go into letters. So A represents 10, B represents 11, C represents 12, D represents 13, and then we have E and F, with F representing 15. Okay, so one of the first ways to recognize a hexadecimal value or number is it's got letters in it. If you ever see any number that's like 0, X12C5, oh, I see a C in there, that's the hexadecimal value. So if I give you that exact same number, 131 here, that's not 131. That's 1 in the 256 values plus 3 times 16, which is 48, plus 1 times 1. So if you add all that up, 256 plus 48 plus 1, that would give us whatever 131 is in hex, convert over into decimal. All right, so there's our little quick tutorial there on hexadecimal. So that being the case, what does that have to do with IPv6? Well, with IPv6, what we're going to do is we're going to take our binary number right here, and every 4 bits, and by the way, you guys probably know that 1 bit is called a bit, 8 bits is called a byte. You guys know what 4 bits is called? Well, if you're a mouse, you know what it's called. It's called a nibble. So 4 bits is a nibble. Let's put that down here. 4 bits is a nibble. Here's another one for you. What if I give you 16 bits? So that would be all of this right there. What is 16 bits called? We call that a word. That is a word. Why do I care, Keith, other than, impressing my friends on Friday night at cocktails? Well, there's a reason for this. You start out and you take your nibbles. Okay, we're going to take a little nibble here, 4 bits, and you're going to ask yourself, what is that value? This is the way I do it. Now, if you can go straight from binary into hexadecimal, God bless you. That's an amazing talent. You're going to be a millionaire someday. I can't do that. So I have to start by going from binary into decimal and then convert the decimal into hexadecimal. So here, 0010, that is 2. Well, we're lucky because 2 in hexadecimal is the same as 2 in decimals. That's 2. This next one here, this next nibble, 1100. All right, that's the 8 and the 4-bit turned on, so that's 12. So 12 in decimal is what in hexadecimal? Hopefully you said C, right? A is 10, B is 11, C is 12. So this would be C right here. The next nibble has got the 4-bit and the 1-bit on, so that's a 5. That's the same between decimal and hex. And then our last one, 1111. If we add that all up, in decimal, that's the number 15. In hexadecimal, that is F. So we've just converted our first word, which is 16 bits, into hexadecimal characters, which is 2C5F. Now that we've got a word, we put a colon and we rinse and repeat. So we're going to have another word. I'm not going to do it right here. And then we're going to have a colon, and then we're going to have another word, and we're going to have a colon. So in the case of IPv6 addresses, because we got 128 bits total, we have 8 words. So 1, 2, 3, 4, 5, 6, 7, 8. Put colons in between them, and that would be your full representation of your IPv6 address. If you take those 8 words in hex and convert them back into binary, you'd end up with 128 bits. Okay, so that's how we represent, that's our beginning of our representation. Let's take a step further right here. Now, if you happen to have an IPv6 address that has a lot of contiguous zeros in it, let me just write one up here, like so. Let's try something like this. 2001 0000 00E3 4000 1234 1234 12 there. All right, so I need 8 of these words. 1, 2, 3, 4, 5, 6, 7. I need one more. 1A0D. Okay, so let's say that this is our IPv6 address, already represented in hex for us. Well, like I said, if you got a lot of contiguous zeros in an address, there are ways to abbreviate it and condense it and make it shorter. So how are we going to do that? Well, start by looking at every single word that starts with a 0, what we call a leading 0. So I'll just put some lines underneath those right here. Okay, so words that start out with leading zeros would be, we've got that word right there, starts with leading zeros. That has leading zeros in it. Okay, the zeros behind the 4, those are not leading zeros, those are trailing zeros, so we can't really count that. It's trailing a non-zero number. These are all zeros. Here's some zeros. All right, and there we go. Okay, so now let's do this. Let's start with a word, our leftmost word, so the one right after 2001 that starts with a leading zero, and let's put a box around all the zeros until they end, all the contiguous zeros, which would be right there. All right, so our next word that starts with a 0 is right here. Let's put a box around that and go all the way to the end where the zeros stop. Okay, now we've identified now 2 sets of contiguous zeros that start at the beginning of a word and run contiguously or continuously until they end. So what we can do is we can take a look at one of these boxes here, just one, and we can represent one of those boxes with a double colon. Now we can't do both, okay? I can't say 2001 double colon E3 blah, 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 double colon something else, because when I type in an IPv6 address with a double colon, remember when I'm typing it into my laptop's NIC card, a router's interface card, whatever, it knows that that whole address needs to be 128 bits in binary. So if I'm using a double colon, that device I'm typing the address into says, okay, there's some missing zeros right here. So let me add up all the binary in front of the double colon, all the binary behind the double colon. What's left? Oh, I'm missing 23 bits. Okay, that double colon must therefore represent 23 bits of zeros. But if you had 2 double colons, which is not allowed, the device would get confused. If I tried typing it in, it would say, okay, well, the first set of double colons, is that supposed to be 8 bits? And the next double colon is 16 bits of zeros, is supposed to be 12 bits and 93 bits. It would have no idea. So you can only use the double colons once. So it makes sense that we would probably want to use the double colons against the box that's the biggest, that has the most amount of zeros. Nothing that says you can't use it against a smaller one, but remember, what's our objective here? Our objective is to shrink this address as much as possible to make it easier for us to deal with. So that being the case, we're going to use the double colons against the second box right here. We're going to use against that. So that means that my address would now look like this once I represent it again. So I would say it's 2001 colon 0000 colon 00E3 colon 4000. And now I put in my double colon to represent that second box, and I keep going. 2A colon 1A0D. So you can see right here, just by putting in this double colon, I've already reduced the size of this address quite a bit. And that double colon represents all these zeros. But wait, we're not done yet. So now with whatever's left, we can go back to our address and say, okay, are there still any boxes left? Are there still any words left that have leading zeros? All right, let's put now some boxes around just the leading zeros in our address. Okay, so in this right here, those first 3 zeros are leading zeros. The last 0, that's the end of the word, right? That's not leading anything. That's the very last hex character in that chunk in that word. So that's not a leading 0. But the first 3, those are leading zeros. These 2 zeros right here in front of the E, those are leading, and that's it. So we're done with leading zeros. So what we can do now is we can remove those from our address and condense our address down to its final form, which would look like this. 2001 colon 0 colon, so I got rid of the first 3 zeros in that second word there, and then E3 colon 4000. Now I've got my double colon 2A colon 1A0D. So that is the shortest we could abbreviate or condense our address. And you can see that reduced it quite a bit from that big, long, massive address we've got on top to the much shorter one on the bottom. Now here's what I'm going to do. This is, like Brittany said, this is being recorded. This is going to be placed on YouTube. So what I'm going to do is I'm going to give you an exercise right now. I'm going to give you an IPv6 address, and I want you to see if you can abbreviate it for me. So if you're watching the recording of this, just pause the recording after you see my address, try to figure it out, and then press play again and see if you come up with the answer I come up with. So here we go. So let's go ahead and delete all this, and let's put in an IPv6 address here that we can actually practice this with. All right, so here we go. 2003.004D. I need 8 words, 1, 2, 3, 4, 5, 6, 7. All right, so I've got 8 words, so there we go. All right, so if you're watching the recording, pause it now and try to abbreviate this. Okay, I'm assuming they've unpaused. We're talking in the future here. Okay, so how would I abbreviate this? So same thing as before. So first of all, I'm gonna put my box around all my words that have leading zeros. There's that one there. There's a bunch of leading zeros there. There's a big, massive quantity of leading zeros there. So I think we can see right from that, that's gonna make sense to use our double colons for this section right here. Now what I'm gonna do is I'm going to get rid of the leading zeros in all the other areas. So I can get rid of those 2 right there. I can get rid of these 3 right there. I can get rid of those 2 right there. And so whatever I have left is how I now format my address. So my address will now look like this. Bring it all out here. So it'll be 2003 4D 0 4A : ED 1, 2, 3, 4. Now let me just double check my work and make sure I got that right. 2003 4D 0 in the 3rd word 4A : ED 1, 2, 3, 4. Yep, so that's right. So that's the correct answer. That is the shortest we can condense that IPv6 address. All right, let's keep moving on here. So that's address representation. Now, when you learned IPv4 addresses, way back in the day when you learned about that, you learned that there were different kinds of IPv4 addresses. So let's go through some of those and compare IPv6 with IPv4. So what I'm gonna do here is I'm just gonna make a little comparison chart. Just draw down the center right there, that looks good. And what we'll do is we'll put IPv4 on the left, because we're all pretty much familiar with that. And we'll put the IPv6 equivalent address on the right. Okay, let me reduce my font size a little bit here so I can fit it in. All right, so let's start out with, so in the world of IPv4, there were different classes of addresses, A, B, C, D, and then experimental. All right, well, that doesn't really exist in the world of IPv6. So I'll just say here, classes, and we'll just say A, B, C, D, and E. Now, when I say that doesn't really exist, that's because there is one kind of equivalent with that. So I'll just say over here, no equivalent of A, B, and C, or E. I'll just say that. So what do I mean by that? What happened to the D? All right, well, we'll get to that. So in the world of IPv4, classes of A, B, and C, all right, if we thought about our A, B, and C addresses, there were sort of subdivisions within those. For example, one of the subdivisions was public addresses. Now, if you think back to your IPv4 days, if I gave you a multiple choice question, I gave you a bunch of IPv4 addresses, and I said, identify from this list the IPv4 addresses that are public addresses. Well, what did you need to do to be able to identify that? You had to memorize something, right? So public addresses, you basically had to memorize just some ranges of numbers. Usually what most people did was they sort of did it in reverse. They memorized what the private addresses were, and then they said, okay, if anything in this list is not a private address, it's probably a public address. Well, in the world of IP version 6, we have public addresses, but we don't call them that. We call them global, actually, if I want to be technically correct, globally routable unicast addresses. That's sort of the long way of saying a public address, a publicly routable address. Now, the nice thing is to recognize a globally routable unicast address in the world of IPv6, it is so easy. You don't have to memorize long lists of addresses. So first of all, I'll show it to you in binary. You might be thinking, what? You're going to write out a 128-bit binary number? Don't worry about it. It's so simple. In binary, any IPv6 address that begins with 001X, and then we don't care about the rest. All right, so we're only concerned about our first nibble here. If the first nibble starts with 001, that, my friend, is a globally routable unicast address. So technically speaking, that means that that first nibble could be a 2 or a 3, right? It could be 0010 or 0011. Well, the IANA, the Internet Assigned Numbers Authority, reserved IPv6 addresses beginning with 3 for future use. Probably in our grandchildren's day, we'll see that. So what this means is that any IPv6 address beginning with a 2, I won't say any, but I'd say the vast majority of IPv6 addresses you'd see beginning with a 2 are these globally routable unicast addresses. Now, why do I say the vast majority? There are a few IPv6 addresses like 2002 and maybe 1 or 2 others that are reserved for special use cases. But if you're ever on a network that's actually doing IPv6 that's routable to the internet, your IPv6 address will begin with a 2. So that is a long way of saying a globally routable address starts with the number 2. All right, so what about private addresses? Let's take a look at those. So private addresses, really can't type today. So private addresses in the world of IP version 4, once again, you had to memorize a range, right? There were a range of addresses. There was anything beginning with 10. That was one of your ranges. There was 172.16 through dot anything through 172.31 dot anything. That was another range. And then of course there was anything beginning with 192.168. Okay, so you had to memorize those numbers in the world of IP version 4. In the world of IP version 6, we have private addresses, although it's kind of funny because there are so many IP version 6 addresses available. I heard someone once say that there's enough addresses that every human being could have enough addresses for every hair on their head, and there'd still be plenty of IPv6 addresses to go around. So that could sort of beg the question, why do you need private addresses? Well, then, we could go down that road, and there's use cases for that. But in the world of IPv6, we don't call them private addresses. We call them, well, depending on the document you read. Initially, they were called site local addresses. So if you read the original IPv6 specification, site local addresses were the equivalent of private. Now we call them unique local addresses. And these are very easy to recognize. According to RFC 4193, if you ever want to read it, this gives you all the details of IPv6 addressing, RFC 4193. Any address that in binary, so I always like to start with the binary, starts with 1111, 110, and then I don't care. So that's equal to, rid of that dot there, that's equal to FC00/7. Basically, any IPv6 address where the first 7 bits in binary are 1111, that's F, 110, I don't care. So that technically could be FC or FD, as in David. But once again, the Internet Assigned Numbers Authority, who's in charge of all these RFCs, they said, we're going to reserve FD for future use. So private, or what we know as unique local addresses, should begin with FC. FC and then anything after that. Okay, now let's pause for a moment. Before we go into the next types of IPv6 addresses, I want to backspace here for a moment. In the world of IP version 4, let's do a new one right here. Okay, so if we had an IP version 4 address that was 32 bits, all right, I'm not counting this up, but let's just assume that that's a 32-bit number there, all right, for IP version 4. So in the world of IP version 4, all of our addresses were subdividable, okay? So, and it was really based on our subnet mask, how we divided it, but it's divisible into 2 portions, right? You probably remember that. So in the world of IP version 4, we had the network portion of the address, and we had the host portion of the address, what we know as the host bits, right? In the world of IP version 6, okay, we still have a network portion and a host portion, but it's a change of name, okay? It's a change of name. You do want to know, oh, my mouse just froze. Okay, let's bring it back here. So in IPv6 land, we want to know the correct terminology. So now in IPv6, we don't really call those bits the network bits anymore. We call them the prefix. And even in the world of IPv4, it's sometimes called the prefix, like especially if you're dealing with routing protocols like BGP, we say we're going to advertise a prefix. We don't really say we're going to advertise a network, although sometimes you do. But the real change is in the last set here. We don't call those the host bits anymore. Those have a completely different name. That's called the interface ID. The interface identifier. Same thing as host bits, but we call the interface identifier. Now, here's another change. Think about an IPv4 address. Okay, think about the IPv4 address you've got on your laptop or your PC right now. Think specifically about the host bits in that IPv4 address. How did those host bits get there? Well, there was really only 2 ways they could have gotten there. Either you went into the NIC card of your laptop or PC and you statically, manually typed in your IPv4 address, which meant you typed in the whole 32-bit number, so you gave it a static network bits and you gave it a static host bits, or more likely, what you did was you used DHCP. But even with DHCP, when you got your DHCP offer from the DHCP server out there somewhere, did that offer give you just your network bits? No, that offer gave you your full 32-bit address, the network bits, and what your host bits were. All right, now let's convert this over into the world of IP version 6. In IP version 6, you still have those same 2 options. I could manually type in an IPv6 prefix and an IPv6 interface ID. For example, if I was to do that inside of a router, it would look something like this. Down here. Okay, so if I was dealing with something like this, if this is my topology, and what I want to do was on router 2 here, gig 00, what I want to do was I want to give him an IPv6 address, and his prefix, his network portion, was going to look like this. So the first half of the address, and by the way, the Internet Assigned Numbers Authority has recommended this. They said, hey, as far as IP version 4 is concerned, your 32-bit IP version 4 number, the end user, the end customer, can pretty much divide that wherever they want. So that's why you see IP version 4 networks where the network is a 28-bit network, or a 30-bit network, or a 22-bit network. The subnet mask gives you the flexibility to have your network bits however long you pretty much want. Now, in the world of IP version 6, you can also do that. Just like an IPv4 address, an IPv6 address requires a subnet mask. Okay, it's got to be in there. So the NIC card, the interface knows, okay, of this 128-bit address, where does the prefix end and the interface ID begin? We need a subnet mask for that. But the Internet Assigned Numbers Authority has recommended in the strongest of terms that all hosts should have the prefix the first half of the address. In other words, our 128-bit address, what you're going to see pretty much everywhere is that all laptops, PCs, smartphones, tablets have a /64, like I've written out here. /64 means the first 64 bits are the prefix, the remaining 64 bits are the interface ID. We're taking our 128-bit address and carving it right down the middle. That is the recommended way of coming up with IPv6 networks, is a /64. So let's say that's what I want right here. Let's say I want to go to router 2, and on his gig 00 interface, which is this interface on the left, I want to give him this prefix, and I want to give him a static interface ID. No problem. All I have to do is go here on a router 2, and that was interface gig 00. So interface gig 0/0, and I would just say IPv6 address 2001 AAAA BBBB, and it was going to be 1212. And now in this case, now I'm going to type in my interface ID. Now I could type in some long number, or I could just say, hey, I want my interface ID to be something really easy, something easy for me to remember. How about a long string of zeros ending with a 2? Because this guy is router 2, so why don't I make all of his interface IDs 0000002? Well, because I got a long continuous string of zeros, I can just have a double colon 2, and now I put in my subnet mask. And here's the nice thing. When you were learning IP version 4, you had to learn about dotted decimal, right? And that carried over to the subnet mask. You had to remember that, oh, a /30 on this piece of paper here means I got to type in 255.255.255.252. You had to remember all those 255 dot numbers. Here in IPv6, we just do a slash and then the number. So the subnet mask is no longer represented in dotted decimal. It's just a slash dot notation. So slash and then a number like /64, enter. Okay, so now I've just given him a static IPv6 prefix. There's the first 64 bits. Remember, this is a word right here. 2001 is 16 bits. So 16 times 4 is 64 bits. And then his interface ID, I've also statically assigned it as a whole bunch of zeros and then a 2. Now, if we were on a host, like a laptop, a PC, a smartphone, we probably wouldn't do this, right? You wouldn't statically give your host an IPv6 address. It would most likely get it via some dynamic method. Well, just like in the world of IP version 4, there was DHCP version 4, there's DHCP version 6. So we could do DHCP and get our IPv6 address as well. However, IPv6 also has something that IPv4 doesn't really have an equivalent. It is called stateless address. Let me just write this on here. I'll give you the acronym for it. SLAC. So normally if you're called a slacker, that's a bad thing. But in the world of IPv6, SLAC is actually kind of cool. It stands for Stateless Address Automatic Configuration. Stateless Address Automatic Configuration. And basically what it is if I have a router running IPv6 on my network, that router can give you an address. And the way stateless address automatic configuration works is that your laptop or your PC or your smartphone, whatever your host is, it's rather complicated. We don't have time to get into it now, but it basically send out a message saying, hey, are there any IPv6 routers out there? I need some addressing information. The router would respond back with something called a router advertisement. And inside that router advertisement, the router would say, hey, here's the prefix. Here's the first 64 bits that all of us on this cable are using. Here's our prefix that we're using. Now you might think, well, that's only half of the equation. My laptop needs not only the prefix, he also needs the interface ID. Well, here's the wonderful thing. In the world of IPv6, your laptop can dynamically come up with its own interface ID. And that is a process that is called EUI64. So that's something I also want to talk about here briefly. Well, we still have a little bit of time to go into that. So let's go back into the whiteboard here. and let's look at EUI 64. EUI-64, which is equal to dynamic. All right, dynamic interface -ID assignment. So that's what we're going to look at here, what EUI 64 is all about. All right, so here's how it works. If I'm using the EUI 64 approach, and when IPv6 first started becoming available in like Mac OS and Windows operating systems and stuff like that, when you enabled IPv6 on your NIC card, this is the method it would use by default to come up with its interface ID. It would use Slack, so it would discover its router. The router would give your laptop or PC its prefix, and then using Slack and using EUI 64, it would come up with on its own its interface ID. And here's how it worked. So I'm just going to do this with the text tool here. So with EUI 64, you start out with your MAC address, and actually I'll do that right here. All right, so the MAC address is the fundamental equivalent of that, or a fundamental component of this. So if we have a MAC address, let's say on my laptop or smartphone of, let's say 021122223333. All right, let's say that's my MAC address. EUI 64 is going to take this MAC address as its base component and convert it into an interface ID. Now remember, we got our prefix. Our prefix was 64 bits. We need the other half, the remaining 64 bits for our interface ID, and yet this is only 48 bits. MAC address is only 48 bits. How do I take a 48-bit number and expand it into a 64-bit number? Well, what EUI 64 does, it says, here's what we're going to do. We're going to take the MAC address and we're going to cut it right in half. All right, and so that's going to give us a number like this, 0211:22. I'm going to put a space here for a second. 22:3333. And in order to give us a 64-bit number, we're going to put a pattern right in the middle, which is FFFE. So this is what EUI 64 does. It takes your MAC address, cuts it right in half, takes the first half, puts FFFE in the middle, and then second half, and now you've got, voila, a 64-bit number. Now don't ask me, why did they choose FFFE? What's the significance of that pattern? You know, if you can find the answer to that, good luck. It's not, you know, it must be buried deep into the dark web or something, but that's the pattern that's used, FFFE. Now, if it was just that simple, oh, wouldn't that be nice? But there's one other little thing it does, which can't really go into the details of why it does this, but we do need to talk about it. So we know that in any MAC address, okay, the first half of the MAC address, which is this portion, is called the organizationally unique identifier, right? Every MAC address, the first half is the OUI. It indicates the vendor or manufacturer of that particular NIC card. Okay, so we have 0211, and then we have 22, so that's our OUI. Now, furthermore, we know that if we take a look at the very first byte, okay, so if we convert that into binary, so 0000, so that's my first 0, 0010, all right, so that's my whole byte right there, 0 and 2. We know that these two bits here on the end also have special significance. That last bit is called the individual group bit, right? So if it's a 0, like this is, that means that MAC address belongs to an individual NIC card. No other NIC card in the whole world is supposed to have it. It's supposed to be individually unique. And if it's a 1, that means it's a group MAC address. Like if I was to send a broadcast, that bit would be flipped to a 1, meaning it belongs to a group of devices. But as far as EUI 64 is concerned, we're concerned about the next bit over. That is called the global local bit. So let's just put this up here. So 0000, 0010. So right here, we're talking about the global local bit. Sometimes it'll be called the universal local bit. But what that means is that, actually I probably should have set that to a 0 because by default it would be a 0. If it's a 0, that means this MAC address is unique. Nobody else has it. It belongs to your NIC card. Now, if you were to go into your router's interface or your laptop's interface, if you were to manually set your MAC address to change it, convention says, the rules of polite society say you should set it to a 1, which means it is now a locally administered address. No guarantees of uniqueness. Well, what does this have to do with EUI 64? Well, in the world of IPv6, when you derive your interface via EUI 64, we put FFFE in the middle of our MAC address to flesh it out to 64 bits, and we take our global local bit, whatever it happens to be, and we flip it. So in other words, if it's a 1 like this, we flip it to a 0. If it was a 0, we flip it to a 1. So if I was using EUI 64, then instead of being 0211, if we flip that, we'd have 0000 0000, right? I have to flip that 1 to a 0. Now instead of 0211, I have 0011. So my final EUI 64 interface ID would be this: 0011 22FF FE22 3333. And of course, you wouldn't see the 00 because that's on the front end. Those are your leading zeros that would be removed. So where you can see this in actual practice is right here. Like this device right here. Okay, let's take a look at router 1 for a moment. So I haven't done anything on router 1 yet. Haven't configured anything. Let's take a look at his gig 00. Show interface gig 0/0. Now notice, here's his MAC address right here. Okay, 0C. So if I enable IPv6 on that interface and I tell him, hey, I want you to dynamically come up with your own interface ID. Well, how's he going to do that? He's going to take 0C798F, and then he's going to put FFFE in there. And then we're going to have 898500. And then what he's going to do, he's going to say, okay, I need to flip the global local bit. So 0C is 0000. C is the number 12, so 1100. Okay, so that's what 0C is. So he's going to flip that bit, which is going to end up being 00001110. Right? That's flipping it. So our final EUI 64 interface ID is going to end up looking like this. Oops, not that. It's going to look like this. It's going to be 0. And now, what is 1110? Isn't that the number 14? And if F is 15, E is 14. So it'd be 0E 798F FF FE 89 8500. All right, so let's see if I'm right. So interface gig 0/0, IPv6 address 2001 AAAA BBBB, and this was 1212::. Now here's what I'm going to do. /64. I'm not going to give him an interface ID. I'm not going to statically assign it. Instead, I'm going to say EUI-64. All right. Show IPv6 interface brief. And there we have it. So there is that prefix I just gave him. And see this? So he truncated the 0, so he left off the leading 0. And there we have our EUI-64 interface ID, just as we converted it right there. All right, so that's how EUI-64 works. Now, however, several years ago, some people made some observations. They said, well, wait a second. if I was, let's say I had the ability to track every single IPv6 address, let's say I'm an ISP, okay, and I'm seeing all the IPv6 packets coming in from all entrance points being various customers I'm connected to, other ISPs I'm connected to. I'm looking at all the IPv6 packets coming in. Now, if all those IPv6 packets, if the interface ID was derived in this way, that would mean that your laptop, well, your MAC address never changes, right? So no matter where you take your laptop, whether you're at work, you're at Starbucks, you're at the library, whatever, no matter what prefix you get, your interface ID would always be the same, wouldn't it? Because it's always based off of the MAC address. So if I'm an ISP and I'm looking at all the IPv6 packets coming in, I'm actually able to say, hey, I'm noticing this interface ID is consistent and it's coming in from Starbucks, it's coming in from Bank of America, it's coming in from the library. So I can track you. I can figure out where you've been because your interface ID would never change if it's based on EUI 64. So for that reason, several years ago, pretty much all the operating systems changed their behaviors, and now all the interface IDs are randomized. They don't use EUI 64 anymore. They use just completely random numbers. And if you actually look in the operating system of your Windows or your Mac device or whatever, you might actually see that you've got multiple IPv6 addresses. Typically what'll happen is you'll once you learn your prefix, that prefix will be, first you'll come up with a random interface ID, and that will be your permanent IPv6 address. In other words, so as long as you're on that network, whether you're on that network for an hour or for a week and you never move, that will be your IPv6 address. But then a lot of times also operating systems will give themselves what's called a temporary IPv6 address. You'll have the exact same prefix because you're part of that exact same wire, that exact same network. Your interface ID will be randomized, so now you've got two IPv6 addresses, both with the same prefix, but the interface IDs are different. Neither one of them has anything to do with your MAC address, but your temporary one is like it sounds, it's only good for a certain amount of time. The operating system might every hour change that, or maybe every 3 hours change that. But the idea is it just rotates over time. You can't predict what it's going to be. It's randomized, the interface ID, but it changes over time. So you might see that. All right, so that's enough of that. Let's just real quickly here run through just a couple of the other IPv6 address types, and then we'll finish up here and give you guys a few minutes to ask me some questions if you have any. All right, so let's get rid of that. Let's go back to this. All right, so just real briefly here, let me just cover some of the other ones. Multicast addresses. Okay, so in the world of IP version 4, we used class D addresses for that, which was 224.anything through 239.anything. Okay, in the world of IPv6, it's much easier. It is FF. Anytime you see an IPv6 address beginning with FF, that is an IPv6 multicast address. Now, of course, that's only the first 8 bits of our first nibble, right? So we still have to have another character and another character before we finish our nibble for that. So just to get into a little bit more details of that. So in the world of IPv6 multicast, we know they're going to start out with FF. This right here indicates whether it's a temporary or a permanent address. What does that mean? Well, you know, if you've been in networking at all, you know there's a lot of networking protocols that use multicast, like routing protocols, right? OSPF uses multicast, EIGRP uses it, RIP version 2 uses it. So those all have permanent multicast addresses. So those would all say FF0. So if it's a 0, it's a permanent or well-known multicast address. However, if you were multicasting a video or something like that, right? This is just, you just need a temporary address just for like an hour or two for this multicast video, then you should do FF1 something, which means it's a temporary address. And these other 4 bits right here in the nibble, actually, yeah, that is what's called the scope of the multicast. That indicates once this multicast is generated on the host device, how far out can it go? And there's different numbers for this. We're not going to go into that. But for example, if you're looking at IPv6 routing protocols, if you and I are two routers, and I'm going to send you an EIGRP hello or an OSPF link state update or something like that, that packet is just meant to go from me to you, right? It's not supposed to go any further than that. That is link scope. So all multicast routing protocols start with FF02. So for example, EIGRP in the world of IPv6 is FF02::A, right? 224.0.0.10 for IPv4, FF02::A for IPv6. OSPF, FF02, 0 because it's permanent, 2 meaning link scope. So the scope is on this wire, no further than this wire, FF02::5 or ::6. That's what you would see for OSPF. All right, so that takes care of our IPv6 multicast addresses. And just one or two others I want to talk about, and then we'll take a break here and so you can ask me your questions. Now, in the world of, there was also something in the world of IPv4, which is called an APIPA address, automatically provisioned IP address. And the world of IPv4, that was 169.254. And then the last 2 bytes were kind of randomized. So this was a bad thing. In the world of IP version 4, if you were on a device and you saw that your IPv4 address started with 169.254, that was like, oh, great. DHCP just failed. Now I got to figure out why that worked. Now, why did you get this address in the first place? Well, the intent behind this was, hey, if you can't get an address via DHCP, if the DHCP server is completely unresponsive, after a few seconds, you can automatically provision yourself with an address beginning with 169.254, and this address should be available on the local link. In other words, routers should not route packets going to or coming from 169.254. If you have other devices on the local link that also have 169.254, you can talk to them as long as they're on the same side of the router as you are. But this is a link local address. It goes no further than the local link. So in IPv4, not a good thing. You didn't want to see this. In IPv6, we have a link local address, which is mandatory. It's part of the standard. So whenever you enable IPv6 on any interface, whether it be a smartphone's radio interface, whether it be a router's Ethernet interface, it will come up with a link local address all by itself. And the way you recognize that is they start out with FE80. Link local addresses always begin with FE80. As a matter of fact, you can see that on my router right here. I didn't really point it out, but notice this, I didn't type this in, but there it is. I typed in the 2001 AABB, but as soon as I did that and I hit enter, the router's interface said, oh, I also need a link local address, FE80, and then it also used the EUI64 method to come up with its interface ID. Now on your laptop, on your tablet, you also have an FE80, and it probably randomized the interface ID. It probably did not use EUI64. So it's mandatory, it's part of the standard, and this is used by a lot of things. There's a lot of underlying things that take place on your link that you don't even know that your laptop or smartphone is doing that utilizes the link local address as its source and or destination of the packets. Okay, and then just a couple of other quick ones because we are running out of time right here. I'll just give you 2 others that you might want to see. So what about the loopback address? In the world of IPv4, the loopback address was 127.anything. 127, the 127 network was reserved for internal loopback. If you sent a ping or a packet to 127, it never left your laptop. It never leaves your smartphone or tablet. It just stays within the CPU. It's like pinging your own brain. And usually the loopback is 127.0.0.1, but technically 127.anything. The whole 127 was reserved for loopback. In the world of IPv6, The loopback is a very simple number to recognize. It is simply : 1. So 127 bits of just nothing but zeros ending with 1. That is the loopback address in IPv6. And then the last address I want you to be able to recognize, and then we'll take a short break here and see if you have any questions, is the default route, what's also called the unknown address. In the world of IP version 4, that was just all zeros. You could have also put a subnet mask of /0 there. In the world of IPv6, you can probably guess what I'm about to do here. That is just : You could put a /0 at the end of it if you want to. 128 bits of nothing but zeros. That is the default router, otherwise known as the unknown address. So for example, if your laptop is utilizing DHCP for IPv6, you're sending out a DHCP v6 message to the DHCP v6 server, the source address you will probably use is just : because you don't have a source address. You're trying to figure out what that will be. So you might see that in a sniffer trace of : All right, so I have taken it right up to the hour mark right here. Let's go ahead and stop at this point, and let me see if there are any questions that I can help you guys out with. Okay, so Tony has a good, not really a question, but more of an observation, which is good. Okay, so Tony mentions, he says, you say that the prefix is always 64 bits, but is it, actually this is a question, I'm sorry Tony, but is it important to know that really the prefix is normally 48 bits plus 16 bits to use for the subnet? Okay, yeah, so if I go to an internet service provider, let's say I'm a brand new company and I go to Time Warner Cable or Charter Communications or Spectrum or something and say, hey, I need an IPv6 network because I want to take your IPv6 network and subnet it and put it on my VLAN 2, my VLAN 3, my IPv phones. What they will give me is a /48. Exactly right. So if I go to this here for a moment. Now, if I'm just a home user, right? If I just need a single IPv6 network, they'll give me a /64. But if I'm an enterprise or a company, they might say, okay, here, Keith, you can have this. You can have 2001 1111 2222 : /48. So they will recognize my company as being that, and then I can take that. Because remember, all end VLANs, all end subnets should be a /64. So I could say, okay, well, everything on VLAN 2, why don't we have that be 2001 1111 2222, and why don't we just say 0002, and that'll be my /64 there. Everything on VLAN, let's say 7, will end with : 0007. That'll be the /64. So you're right. I'm starting out with a /48. That's what my service provider gave me, which means that the next 16 bits, and remember with 16 bits you have over 65,000 combinations of numbers you can get. I can come up with over 65,000 unique IPv6 subnets, all of which will be /64s. So thank you for pointing out. Very good. Very good question. All right, what else do we have here? So a question from Karmank. Says, if you enable EUI64 on a router, will it act like a DHCP server? Short answer is no. So first of all, to act like a DHCP server means that when a DHCP message comes in, and by the way, in the world of IPv4, if I'm a client, my first message is called a DHCP discover message. Well, in the world of IPv6, I believe the first message is called a DHCP solicit message. It's basically the same thing as a discover. It means, hey, is there a server out there? I need some information. That's a DHCP solicit message, a DHCP v6 solicit. But still, a router will not respond to that unless you manually configure the router as a DHCP v6 server. Okay, so he won't do that. He won't respond to DHCP v6 messages. As a matter of fact, by default, he'll drop them. Just like by default, he'll drop DHCP v4 messages as well. So when you go onto a router's interface and you say EUI 64, all that's saying is, hey, I've given you your prefix. I typed in IPv6 address. I gave him the first 64 bits. And now by saying EUI 64, that just says, hey, router, on this interface, I want you to come up with your own interface ID locally. It has nothing to do with how he will respond to clients or what he will or won't do with clients. It's just for the purposes of him dynamically coming up with his own interface ID. Okay, and Bashar asked the question. He says, I'll write this right here like this. He says, hey, when I go onto my device, I see that I've got an address that looks something like this. It looks like FE80, so that's your link local address, and then some numbers, AB70, you know, whatever. But then he sees something weird. He says, then I see a % sign and like a number like that. And he's asking, what does that mean? So this is referencing the interface where that address was configured. So for example, you know how, like I'm running on a Mac. I've got a MacBook here. And in the MacBook, I'll actually show you this right here. Let's see, how do I get rid of this? Get rid of that. Okay, there we go. So hopefully this isn't too small for you guys. If not, I'll read it. If I do ifconfig on the MacBook, okay, see how my interfaces have names like EN1, EN2, EN0, right? You see that? Well, I don't know if you guys can see this. I don't know if, I'm sorry, I'm not proficient with terminal, so I don't know how to increase the size of this font. But it says iNet6, FE80, okay, and then it says % EN0. So that means this particular address has been allocated to that particular interface. So in your case, if you see like %5, that means interface number 5. So you'd have to somehow figure out, okay, is that my Ethernet interface? Is that my Wi-Fi interface? But every interface in your particular system has a number allocated to it. And that's saying that address has been allocated to that particular interface. So that's what that means. Great, good question. Will there be a follow-up class for this? I don't have any plans for follow-up class, but if you're interested in a follow-up class, or there's something else you'd like to see from me, my email address is kbogart@ine.com. You're always welcome to send me your suggestions. That's kbogart@ine.com. How to subnet IPv6. Oh, I wish we had time to go into that. We just don't have time for that. However, that does bring up something else I can show you real quickly here. Let me go back to this. For the things I did not cover, we have a ton of great videos dealing with IPv6. If you go to streaming.ine.com, whether you've got an INE account or not, anybody can go to streaming.ine.com. If you type in IPv6 in the search field, there's a lot of stuff in here we have from me as well as a lot of other authors, courses and individual videos on IPv6. So a lot of the stuff in here would answer that. For example, IPv6 subnetting, I would expect to see that, well, introduction to IPv6 should have it. IPv6 design should have it. So a lot of these things in here would talk about IPv6 subnetting. I would expect them to be in there. So if you don't have an all access pass from INE, I would definitely recommend you get one because it'll give you access to all these videos plus hundreds, if not thousands of other videos we've got on all sorts of topics. Okay. And Kim asks, are we able to route /64s and BGP on the internet or only /48s? That would be really up to the service provider's routing policy. I would suspect service providers probably don't want to route /64s. Some may be doing that, but I would suspect they're probably routing /48s or in some cases even /32s. Your intro text stated that regional authorities are out of IPv4 addresses. Is that just in the US or globally? Globally, I believe that there are no more regional internet registries that have IPv4 addresses left. I think globally they are gone. So the remaining IPv4 address space is now owned by individual service providers who gobbled them up before the regional internet registries ran out. Okay, so let's just take 4 more questions here. Okay, so Faikal asks, from this address FC00/7, what's the first prefix ID? You can make your first prefix really anything. So if we're dealing with a private address, let's put this on here. Okay, so let's say that I had something like this here. Here's my router, router 1, and I've got 2 links, maybe going to some labs like lab 2 and lab 1, and I want to assign unique local, otherwise known as private, addresses to these. So we know that each one of these is going to have to start out with FC. But sticking with convention, where /64 is what your end hosts should be, then I could do something like this. I could say, all right, well, on this one right here, why don't we just say everything on there is going to be FC00 :0:0:1. That could be my first. Actually, technically, you can have like that. So that could be my first prefix, my first private prefix, and this one over here could be 0:0:1. That could be my second available unique local prefix. As long as the 64 bits are different patterns, one is uniquely different from another, routers would be able to tell that they are different 64-bit prefixes and be able to route between them. All right, 2 more questions here. In IPv6 multicasting, is this a valid address? Okay, so the addresses given in this question were FF11:1 and FF01:1. Okay, are they valid addresses? Well, yeah, they're valid addresses, but they mean 2 different things. So remember that this bit here, so if I flesh it out here a little bit, FFX, and then this bit right here is the scope. You don't really want to set that to anything less than a 2, right? A 2 means link local scope. If I want to put a multicast packet actually on the wire, and I want to stay on the wire, go no further than the router on the wire and everybody else on the wire, that would be FF something 2. FF something 1, that is kind of like pinging yourself. It doesn't even really go on the wire. That's, I have a note here to myself about that one. That scope has a weird name. That is called interface local scope. So not sure why you would do that. And then the second bit here, so this one right here, is temporary or permanent. So basically what this is just saying is this one says this is a temporary address I'm using to essentially ping myself, multicast to myself. It's not even going on the wire. It's going to go down to my NIC card, and that's as far as it's going to go. And it's temporarily assigned. And this is a permanent address because it's FF0. That once again, I'm just keeping it on my own interface. It's not going anywhere. So that's what those addresses, that's how those addresses would translate. All right, one more question and then we'll wrap it up here. Actually, there's only 2 questions left, so I'll hit both of your questions. So the last 2 questions are, can a unique local also start with FD. Here's the deal, okay? Think about, all right, the correct answer would be no, that FD has been reserved by the Internet Assigned Numbers Authority for future use, that you should really just use FC. But let's think about it in reality, right? Think about the world of version 4 for a second. If I have a private network, okay, let's say I have a lab network somewhere, and I say, okay, packets originating from this network are private, meaning they should never go to the internet. Well, yeah, convention says I should address that private lab network with 10 dot something or 192.168 dot something, right? But in reality, I can pretty much give that lab network whatever I want as long as on my internet router, I'm filtering it, right? As long as my internet router knows what that lab is and is preventing it from being routed outside, I'll keep it private. Nobody on the outside will learn about it. So, hey, why not give my lab network, 122 dot something? Yeah, that's probably owned by somebody out there in the world, but as long as I'm filtering it, I'm preventing it from going out, hey, that's the main goal, right? Same thing in IPv6. Will your router blow up if you give it an FC address versus an FD address? No, it'll take it. It won't complain. It's just that you're now sort of out of conformance of what the Internet Assigned Numbers Authority says you should be doing. But once again, you're not going to be routing any packets to the internet anyway that have FC or FD as their source address. You should be filtering that on your outbound router. So you can do it. No one's going to jump down your throat, but technically speaking, the IANA says you should really use FC, not FD. And then the last question for today. I missed some of the meeting, but what about NAT with IPv6? Is it still supported and or used? It is. It is still supported. There are, at a real high level, there's two flavors of NAT when it comes to IPv6. One way is to take an IPv6 address and NAT it or convert it into an IP version 4 address. And there are multiple protocols that do that, like NAT64 and NAT-PT and other stuff like that. And then there's another way where you can actually use NAT to take an IPv6 address and translate it into another IPv6 address. That's called NAT66. NAT626 or just NAT66. All right, so yes, that does exist. There are some use cases for that. It does exist and it is supported. Absolutely. All right, everybody. So that brings us to a close for today. I hope this was a really meaningful and useful webinar for you. I hope you got a lot out of it and learned some things you didn't know before. And thank you, everybody, so much for attending, and we'll see you in the next INE webinar. Have a good week.